All right, I think it's time. We should get started. So this class, we're going to learn a new particle control device. It is called Cyclones. So you guys can see my slides, right? Good, okay. So it's called the Cyclones. And so last class, we learned about the settling chamber, which is just using gravity to settle down particles. And we mentioned that it is a passive method, right? We're not going to build a chamber to remove the particles. It's basically it's happening during the transport of the flue gas. So it can happen during the inside the duct when we move the flue gas from one location to the other location, right? So just a brief recap. So basically, we learned that for all of these settling chambers, well, I think it's getting stuck again. Just a moment. Open that again. Okay. Yeah, so for all the settling chambers, we mentioned about single particle size, multiple size, or continuous or discrete, but all of them are using the same principal equation, which is matching the drag force with the gravity, right? 3 pi mu dp divided by c multiplied by vr, right? For settling, we don't have a, basically the air is stagnant, right? At least in the direction of the settling direction. So that's why the vr can directly be the settling velocity, say vt or vs. Okay, so this is just the particle velocity that's settling down, right? So we mentioned about the tilted duct, right? Pointing upwards or pointing downwards, the situation might be a little bit different. And then basically for a continuous size distribution, then that will involve the integration of the removal efficiency. So here, I think we can spend some time to do a quick quiz about calculation of the particle removal efficiency. Let's see here, set it up. All right. So it's a simple calculation here. Let's spend maybe 1 or 2 minutes to work on this, right? So basically it's saying that in a settling chamber, we have particles of 2 different sizes. Because the smaller sized particles have a lower gravity, right? So the removal efficiency is lower. Well, for the heavier particles, the removal efficiency is higher. You can take your time. You can maybe spend 2 minutes or 3 minutes on this. I think most of you have got an answer. So remember, when we calculate the removal efficiency, specifically for the 2 different sizes, we mentioned that it can be calculated by M1 plus M2 on the denominator, M1 eta 1 plus M2 eta 2, right? Hope this is not blocking the equation. Okay, 10 more seconds. Okay, we'll stop here. I think we just have one student who didn't submit the answer. So most of you guys are correct. It should be 50%. So basically, we just plug in the mass concentrations, right? So it's 100 here in the denominator. Basically 100 plus 100, and then 100 multiplied by 30%, and then 100 multiplied by 70%, right? So finally you get 50% in terms of overall particle removal efficiency. So I would say that this setting here is a little bit, it's quite straightforward, right? So basically you have both concentrations at 100. Let's say if we change one of the concentration to 50 microgram per meter cube, then you also have to change that in here, right? So the answer will be quite different. So basically it's not 100%, right? So because you're not achieving 100% for either of the sides. So that's why the overall efficiency have to be below 100%, okay? So this is just brief calculation in terms of the particle removal efficiency. I think in this class, in the calculation of the cyclone, you'll get more understanding regarding this overall removal efficiency. All right. So now let's start with the new contents. Okay. So here I'm showing a few pictures of the cyclones. So whenever we mention cyclones, we'll say it's something similar to tornado, hurricane, or typhoon. Depends on where you live in. People have different names for these rotating systems, right? So typically the air, let's say the air will rotate inside, right? And will form these rotational movement of the airflow. So I'm not sure if you have seen a typhoon or seen a cyclone very in close distance. I have never done that. I think it should be quite dangerous. Okay, so but I'm pretty sure that we have watched it on movies or on TVs. I know that there are people. If you see the Weather Channel, there are people chasing the tornadoes, chasing the hurricanes, right? So here I'm just showing a screenshot of a movie. I like this movie quite a lot. It's the Day After Tomorrow. It's about climate change and some science fiction, right? And although it has a pretty low rating, I don't know what's the reason, but I think it's quite amazing to show what is the impact of the climate change, right? So they're showing several hurricanes or several tornadoes just over the cities, right? So if you watch those videos, you can see that typically the larger objects will get spinned out, right? So I had the impression that some of the tornadoes, they might draw the cars up to the sky and then get spinned out. Right? Let's say the larger particles or larger objects will just get spinned outside. It's similar to the washing machine that we use, right? At the high speed, the water is spinned out. So the reason why these larger objects can get spinned out is because of the force balance. Okay, so we know that if any object wants to do this rotational movement, they have to have a centrifugal force. Basically, a force have to support the particle to rotate, or the object to rotate around the center. So for example, if an object rotates in this way, then there should be a force that's providing this centrifugal force, right? So for these larger objects, because they're so large, right, then we know that centrifugal force is basically F equal to mv squared divided by r, right? So at the same velocity and same radius, the heavier the object, the larger the centrifugal force. So basically these larger objects, they don't have enough of a force to support that centrifugal force. So that's why they will leave the rotational movement. They will leave the cyclone here, right? So we can use the same mechanism to remove particles. So I'm not sure if you go to, you have been to some industrial plants or power plants. So there you can typically see these devices, these ones. So it's mainly composed of a cylinder, that's at the top, and then you have a cone at the bottom. Okay, so what happens is that the air will enter from side of the cyclone. So this is called a cyclone. Enter from the side of it, and then get introduced into this cylinder here. So what happens is the air is going to, let's say, the air is going to rotate, right? So the heavier particles or the larger particles, because they don't have enough of a force to support the rotational movement, they will just get spinned onto the wall. On the wall, you will collect larger particles, and then because of gravity, they will just fall down along the wall, and then finally get collected at the bottom, right? And for these devices, typically at the top, there's also an outlet. Okay, so the outlet will draw the airflow outside. So we mentioned that the air will enter from side and then get drawn outside. Okay, so in this way, we can basically introduce particles into the system and then withdraw the remaining airflow from the system. So there's a mass balance of the airflow, right? So here I can basically show you a video about the working principle of the cyclone. Let's do this. So can you hear the, yeah, maybe not yet. Let me do this. Let's see. All right, so you can see the video here, right?
Hurricanes are customized cyclones to serve different needs and which results from optimization functions such as maximize efficiency, minimize cost, or minimize size. Combining stochastic numerical optimization by changing the 8 independent cyclone dimensions with the knowledge of particle agglomeration, ACS is able to design the perfect geometry for each case. The colored dots indicate the particulates to be collected, and the blue arrow represents the flow of gas that leaves the equipment. For dusts with tendency to agglomerate, such as biomass or coal fly ash, among others, efficiency is maximized thanks to the clustering effect of particles. In fact, the cyclone doesn't see as many small particles, but clustered particles with bigger dimensions and thus easier to collect. Agglomeration increases with wide particle size distributions, long residence times in the cyclone, and large inlet particle concentrations. Agglomeration is maximized with the new developed Hurricane MK cyclones. Emissions can be under 15% of those of other cyclones, being as low as 30 milligrams per normal cubic meter for many industrial processes.
Okay, so this is a commercial for a cyclone system, and they call it hurricane or tornado or typhoon. So basically, they're in general in industry we'll call them as cyclones. Okay, so you see the major mechanism is that the larger particles, because of their larger mass, they will get spin outside, right? So finally, you can collect them. So there's also a quite interesting video about a homemade cyclone. So if you have a vacuum at home, so you can actually make this one. Yeah, you see the airflow, the particles. So there's actually a quite interesting phenomenon. So you see when the air draws inside, it actually flows like a band, right? Because the air is incompressible. So they flow like a ribbon, and then they just stack on each other, right? Then finally, when they get to the bottom where there's a cone, they have to get compressed, And then this is the outlet, right? So the air is withdrawn from the top. You can see how the yeah, so this is the basic principle of a cyclone. Let's get back here. So I think maybe most of you know that our school used to have a coal-fired power plant. So last year, actually last December, and so our school decided to decommission the power plant, right? So I was a little bit upset about that because whenever I teach the class, I'll use that power plant as an example. So see, that's a stack, right? And then there are cyclones built with that system as well, because our class is about air pollution, and coal-fired power plant is a basic example of showing where we should put or how we should control the PM coming out of the photo combustion. But I did manage to take a few pictures of the power plant. So I didn't take this one. I guess this is going to be quite dangerous to take. But you see that actually last December, we started to dismantle the high stack, which used to be a landmark in Rolla. Okay, so I'm not sure about the remaining parts, but maybe they managed to leave a few parts still at the original site. But at that time, so I took this picture. At that time, the cyclone is located on the side of it. It's here. Okay, so you see that it's right before the stack. I think there are further PM control devices after the cyclone, because later you'll find cyclone is still not as efficient as compared to other PM control devices. But this is a direct way you can process the particles coming out of the combustion chamber and then remove the particles. Okay. So here are a few other pictures of the cyclones. Cyclones can be large, can be small. You can design different dimensions of it, right? So if there's a large scale coal-fired power plant with a really high power or capacity, then we can build more cyclones or build larger cyclones to remove the particles. So there are a few advantages and disadvantages of the cyclones, and it's actually quite straightforward to understand these, right? So if you think about the structure of the cyclone, it's just composed of a case, right? A stainless steel or metal case. We don't need to add in any other rotational parts, right? We can just build it as is, and we just need to worry about the leakage. There's no leak for the setup, right? So that's why it has very low capital cost. So, I mean, we can even build a homemade cyclone, right? So it can operate at high temperatures because the case is made of metal, so it can withstand high temperatures. It has low maintenance because there's no moving parts. We don't need to disassemble that, replace parts inside, because basically there's no parts inside, right? It can handle liquid mist or dry materials, right? Later we'll know that for some PM control devices, it cannot control high relative humidity particles because it can just block the device, right? It can collect dry aerosols, or dry solids, or liquid materials. Either way works, right? And also it needs relatively small space for installation. This is mainly because the airflow going through the device has a very high speed, right? To maintain that high speed, the device have to be small. If the device is too large, then it's going to create a high pressure drop. So there are also a few disadvantages of the cyclones. So for example, the most important one is that it has low efficiency for very small particles. So there are some values in terms of the remove efficiency. So in terms of the overall PM efficiency, let's just use it this way. So in terms of all the particulate matter, we know that there are very large particles. So large particles, they have heavier mass, so they can get easily removed by the cyclone. So in terms of the overall PM removal efficiency, that's somewhere around 70 to 90%, which is not bad, right? So we can get rid of most of the particles. But if we further zoom in to PM10, then that efficiency is 30 to 90%. Depends on the structure. And if we talk about further smaller particles, that's just 0 to 40%, PM 2.5. So the cyclone doesn't work very well. So under this situation, we have to use some other devices to remove very small particles. So here you can also see that how people will show the overall efficiency. So a lot of coal-fired power plants, when they talk about their PM removal efficiency, they will say that the removal efficiency is 99.9%, but that is the overall efficiency, right? So in terms of the very small particles, the efficiency can be very low. And these small particles, because they can suspend in the air for a longer time, so they can put a more health damage to human. So you can, from those words, you can basically understand people try to bring up their highest efficiency, but in details, it might not look very good. Okay. So the other disadvantage is that it has a high operating cost because of the pressure drop, because we have to pull the airflow through the cyclone. So that's why we have to put a fan downstream of the cyclone to draw the air going through, right? And sometimes, so basically because of the centrifugal force, the higher efficiency we want, then the higher the speed the particle should be, right? Because again, the centrifugal force is mv squared divided by r, right? So if the velocity becomes higher, then the centrifugal force will become, or the required centrifugal force will become higher, which means that smaller particles cannot sustain them in the rotational movement. So that's why we have to bump up the speed. But once we bump up the speed, then the pressure drop will become higher, right? So it's going to take a cost more in terms of managing or maintaining this device. The third disadvantage is that it's unable to process sticky materials. So it's also quite straightforward. If particles is very sticky, it's just going to stay on the wall. There's no way we can collect them at the bottom. Okay. So here I'm showing a few schematic diagrams of the cyclone. You can see that the internal structure is also quite simple. So basically, the air is introduced from the side of the cyclones, right? And then after it enters, it's going to have that rotational movement. So I also mentioned that, for example, in that homemade cyclone, you can see that the air actually moves similar to a ribbon, right? So it's not going to compress or basically stack on each other, but they have to align very well because the air is not compressible in here. So that's why when the air first come in, it's going to rotate, and then it has to go further below, right, in this way, and then further go below here. So at the bottom, because of the conical shape, so there's no more space for the air to further move down, right? And then at this time, the air will just come up, mainly because the outlet is here, right? The outlet continuously draws the air from here, right? So the air will finally come up. So in terms of the efficiency of the cyclone, so you can see that basically the efficiency would be determined by how many turns it makes in the cyclone, right? So if we make a very long cyclone, have a very long cylindrical shape, then it can make more turns, right, before it's introduced outside, right, before it's emitted outside, right? So the more these turns it can make in the cyclone, the higher the efficiency. And actually, the number of turns is dependent on just a few parameters, right? So we mentioned that the air will move as a ribbon, right? So the number of turns will just be dependent on the height of the airflow that's being introduced, right? And also what is the height for the entire cyclone. because the longer the height, the more turns it can make, right? So we call this turn, we use a parameter called NE. This is the effective turns. So the effective turns can just be calculated by LB plus half of the LC divided by H. Okay, so LB is the cylindrical part. Okay, LC is the conical part. Okay, so height of the conical part. So we can just use this height and then divide by the height of the inlet flow to calculate how many turns or how many effective turns the air can make in this cyclone here, right? And then the other thing that will affect the collection efficiency is the velocity. Okay, so the air velocity. We know that the air will be introduced in this way, right? So if we look in this angle, the air will go inside, right? The air will go inside. So that's why we can see these crosses, basically the arrow pointing towards the screen, right? And then the air, after getting inside, is going to rotate it this way. So the velocity of the air will also determine the efficiency. I mentioned that the higher the velocity, the higher the efficiency, right? Because the higher the velocity, the higher the centrifugal force. So this velocity here, people use VI, basically means the inlet velocity, can be calculated by just the flow rate divided by the cross-section area of the inlet. So it's just Q divided by H multiplied by W, right? This makes sense. I have the flow rate divided by the cross-section area, that's the velocity, which is the inlet velocity. So basically with these parameters, we can try to solve for what is the collection efficiency of the cyclone, right? So this is the equation that people come up with. So for each design of the cyclone, people define a parameter that's called the cutoff size. So this is a critical size for a cyclone. So basically, if the particle has a size that's larger than this critical size, then it's going to have a higher collection efficiency. But if the particle have a smaller size, then the efficiency will become lower. So this critical size is calculated by this equation. So it looks quite complicated, but we'll show what is the reason it has this form. Okay? Because now we know the equation for the drag force. It's actually quite straightforward to solve for this equation. So on the right-hand side is the equation that calculates the removal efficiency. Okay, so the eta here. So this is the removal efficiency, or the, let's say the removal. So the removal efficiency is specific for a particle with a size of dpj. Okay, so I already solved the dpc here. You see the dpc is just the equation here. Okay. Maybe I should leave some time for you guys to write down the equation. Okay, so this is the cutoff size, dpc. So for each, basically for each of the cyclone, it's going to have a specific cutoff size. So we have to put in the parameters. So you can see that the parameter is dependent on the W, which is the width of the inlet, right? Mu is the viscosity of the air, and E is the number of effective turns we just introduced here. Vi is the inlet velocity. Rho P is the particle density, and Rho G is the air density. Okay, so with these parameters, we can solve for what is the cutoff size, right? And the second equation here basically use this cutoff size. So if we know particles of a specific size, then we can calculate what is the removal efficiency. Okay. So let's say for example, for a cyclone, we find out that this cutoff size is 5 microns. Basically, we'll plug in some numbers later on. Let's say for a cyclone, after we plug in the numbers, we find that this size is 5 microns. What we're going to do is to plug in this 5 micron to here. Here, we'll put in 5 microns. And then for this size, it's any size that we're interested in. Okay, so for example, if we're interested in the collection efficiency of 5 micron particles, okay, so we introduce 5 micron particles into this cyclone and then operate it. So what's going to be its final efficiency? E of 5 micron is going to be equal to 1 divided by 1 plus 5 divided by 5 squared. Okay, that's 50%. You can see that the cutoff size is just the size that has 50% of the removal efficiency, right? So now let's say that we're interested in 10 micron particles. So either 10 micron is going to be equal to 1 divided by 1 plus 5 divided by 10. Okay, squared. So that's 1 divided by 1 plus, this is 0.5, right? So 0.5 squared, that's 0.25. 1 divided by 1.25, right? So that's going to be 80%. So you see that from this equation, we can get a general trend. Let's say that what's going to happen if particle size increase? If it increases, the efficiency is also going to increase, right? So let's say for an extreme example, right? So we talk about particles of a few microns. Let's say we'll use our classical example of a particle. We'll use a potato, okay? So let's say we put a potato inside. Because the size is too large compared to the critical size. So this term will go to almost 0, right? 5 micron divided by a size of a potato, and then you further square it. So this term will go to almost 0. So that's just 1 divided by 1, which is 100%. Okay, if the size goes to extremely large range, then the efficiency is 100%. But what happens if we talk about very small particles, right? So dpj decrease. Let's say if the particle is very small, we're talking about 1 nanometer particle, or even air molecule. Air molecule is a few, maybe a few tenths of, maybe point something nanometer, 0.1 nanometer, let's say. Then dpc divided by dpg will be very large, right? And then you further square it, will become more, basically much larger, okay? Infinitely large. So 1 divided by an infinitely large number will go to 0, which means that for small particles, the collection efficiency will be very low, okay? So now you can see how this equation makes sense. So basically, first, to decide a collection efficiency of a cyclone, we first need to find out what is the cutoff size. And then with that cutoff size, we can calculate whatever efficiency for a specific particle size, right? So here I have another video trying to show you basically particles with different sizes. They're going to have different collection efficiencies. And this is for a CFD simulation result. Okay, so you're introducing particles of 3 different sizes: 1 micron, 5 micron, and 10 micron. Okay, so the 1 micron ones are just blue ones. So you see, because of their smaller size, the small particles will just follow the flow, and then they can easily get exit from the cyclones. While the larger particles, they will just stick to the wall, and then finally get collected at the bottom, right? So basically from the simulation, you can calculate what is the collection efficiency for particles with different sizes. And then actually agrees very well with the experiments, right? So basically particles with different sizes, they're going to have different collection efficiencies. And then, as we mentioned before, for example, this equation, this DPC equation here is very complicated. And because now we know the equation for the drag force, we can actually try to prove why this size is the critical size, okay? So let's say, for example, if we just draw the cross-section view of this cyclone, okay? Let's say we look from the top, all right? So what's going to look like from the top is basically a cylinder, going to be a sphere, it's going to be a circle, and then this is our air inlet, right? So after the air is introduced, it's going to rotate in this way. And finally, this is the outlet of the air, right? So we mentioned that for all the particles that rotates like this, we have to provide a centrifugal force, right? So it's like we put a string and then connect a string to a sphere, and then we spin it. So the force that we drag we pull the string is going to serve as a centrifugal force. So for a particle to move like this, move in rotational directions, we also need to provide a centrifugal force, right? So where is going to be that force, or what's that force? Because basically the air after the particles are introduced in the cyclone, there are no more surfaces or no more mechanism to provide this force, right? But one thing we know for sure is that the particles are going to move across the flow, because let's say the particle wants to deposit here, then it has to go across the airflow, move like this, okay? So basically there's going to be a relative velocity between the particle and the air in this direction, right? The particle wants to move from this location to the wall, right? And then there's going to be a relative velocity between the particle and the airflow that's in the radial direction, okay? So once there is a relative velocity, then we know that there's going to be a drag force. So the drag force is going to try to pull the particles towards the center, okay? And this drag force will serve as the centrifugal force. So that's where the centrifugal force come out, right? So basically, what we can do is we can equate this drag force with the centrifugal force. So this is going to correspond to the a particle with a critical size, right? It's going to maintain itself in this rotational flow here. So we know that the centrifugal force is mvi squared divided by r. So vi again is the inlet velocity equal to drag force 3 pi mu dp divided by c multiplied by vr, right? So this is how we set up the force balance here. So let's assume that here the particles are very large. So let's ignore this c term. Okay, typically the cyclones can treat particles of a few microns. So that's why we don't, a few microns is much larger than the mean free path. So we can just treat this Cunningham correction factor to be 1. So what we can have is just mvi squared r equal to 3 pi mu dp multiplied by vr. So again, this vr here, or the relative velocity here, is just the velocity that the particle tries to go across the flow, right? So let's say we set it as vt. Okay. Again, we can put in the expression for m. M is pi over 6 dp to the third multiplied by rho p. Okay, we have vi squared r equal to 3 pi mu dp vt. Okay, so dp can get cancelled here. We have 2 of the dp's, right? So if we just solve with this equation, it's going to have so pi and pi can get cancelled. We have 18 mu vt r divided by rho p vi squared. Okay. If you compare these two equations, okay, so they are still a little bit different, right? So now we have the mu term here. Okay, so we can get at least we made a, or we have the particle density term here. So we made some progress here. So the thing is that right now we need to plug in the Vt and Vr, right? So Vt and Vi. So we know that the Vi is just the Q divided by H multiplied by W. That's the inlet velocity, right? And then we just need to find out what is the Vt. So Vt again is the velocity of the particle that goes in the radial direction, right? So that can be solved from in terms of the movement or in terms of the trajectory of the particle. Let's say the particles will spend the time of delta t in this cyclone. So one thing we know for sure is that, let's say the particles finally get collected, then Vt multiplied by delta t should be equal to W. So W is basically this distance here. Right, this is W, because we know that if the particles can get collected, then it has to enter from here and then spin all the way to the outside, right? So this is a radial movement. This is a radial movement of the particle, which is W, right? So at the same time, we know that in terms of inlet velocity, Vi multiplied by delta t, that's basically how many turns the particles can make, right? So that's going to be Ne multiplied by pi multiplied by d. So we mentioned that Ne is the effective turns the particles make in the cycle, right? So Vi multiplied by delta t, that is the total distance, basically the total distance that the particle make in terms of the rotational movement, okay? So we have these two equations, right? So now we know that basically if we divide these two equations, we can just cancel the delta t. That's going to be W divided by Ne pi d. Okay, so now let's look at this equation again. Okay, we have this equation. Right, I'll just put it here. So dp equal to square root of 18 mu. So Vt here, we know that Vt is equal to W divided by Ne pi d multiplied by Vi, right? So we can plug that in. So that's going to be equal to, let's see here, W Vi R divided by rho p Vi squared Ne pi d. Okay, we can cancel a few terms. Vi and Vi can get canceled, right? R is just half of d, right? We have 2 here. So that's going to be equal to 9 mu W divided by rho p Vi pi. Okay, So now if you compare these two equations, so this is what we have, right? And this is what people determined from the simulation or from the experiments. Okay, so you see that we have most of the terms ready. So 9 mu w, 9 mu w. We have pi ne rho vi. All of these terms are ready. So finally, people decided that we need to put a 2 here to make it more accurate. But a square root of 1/2 is not a huge value, right? It's just a small modification in terms of the final value. So now you can see basically by using the force analysis, by using the drag force, we can solve for what is a critical size of a particle in the cyclone. Okay. So in terms of the real design of the cyclone, or the real industrial application of the cyclones, people won't come up with their design randomly. So here it's showing a table. So this is showing the classical cyclone dimensions. And people can choose whether they want high efficiency cyclones, or conventional cyclones, or high throughput cyclones. So high throughput cyclone just means that you have a high flue gas flow rate. The flow rate is too high, so you have to let the air to go through at a high throughput, right? So these ones will not have a high efficiency compared to these high efficiency ones. But most of the cases, people will just use the conventional design. So you can see that the conventional design is basically giving you a list of, so either 3 or 4, number 3 or 4. And it's giving you a list of ratios that you can choose. So for example, you decide that your diameter of the cyclone is 1 meter. Okay, so then you can find out what is the height of the inlet. So the h here, right, h over d is 0.5, so the height can be 0.5 meters, right? The width of the inlet is 0.25, so that's 0.25 meters. So everything is ratio, or everything is non-dimensionalized by the body diameter, which was assumed to be 1 meter here, right? So the diameter of the gas exit, so here, dE divided by d, 0.625. So that's going to be 0.625 meters, right? It really depends on what is the body diameter. If it's half a meter, then all the diameters will change, okay? So for this conventional type, people also call that as a LAPO type. So it's just a name, right? He came up with this design for the cyclone here. So here we know that once we know the dimension, and if we know the flow rate, we should be able to calculate what is the critical size, or what is the cutoff size, right? We just need to know what is the air viscosity, right? The width of the inlet, the particle density, the inlet velocity. Right? Inlet velocity is just the flow rate divided by the cross-section area of the inlet, right? And the number of effective turns. So the number of effective turns we already showed here. It's dependent on the cyclone dimensions, right? So with all of these parameters, we can try to solve for what is the collection efficiency at different sizes. So this is an example trying to look into what is the collection efficiency of particles of a conventional cyclone, which is using the LAPO type of dimension. So we'll go through this calculation process in more details in our next class. But if you have time, try to go through this process in advance. It's going to be more easier, help you understand this problem, right? So basically we have different sizes. We need to calculate what is the collection efficiency at all different sizes, all right? So that's all for this class. Let me know if you have any questions, all right?